All right, so we've got a geothermal heat pump. I've got my diagram here. On the bottom, we've got our evaporator, and that's where the geothermal part comes in. So you've got well water coming in at 55 degrees Celsius, giving heat to the cycle, and then being discharged at a lower temperature. Up at the top, if you look at the condenser, you see that's where the heating is going on. So you've got heat being rejected from the cycle, going into the air to heat the air. All right, so the first thing that we're supposed to find is the volumetric flow rate of heated air to the house. So what I've done here is I've designated 70 degrees and 110 degrees Fahrenheit to be TA1 and 2. I've also designated a volumetric flow rate of the air at 1 and 2. And what we're interested in is the volumetric flow rate of the air to the house. So that would be V.A2. We also want to find the isentropic compressor efficiency, the compressor power, the coefficient of performance, and then the volumetric flow rate of the water from the geothermal wells in gallons per minute. So if you look at the bottom here, this is the flow of the water through that evaporator. I've designated 55 degrees Fahrenheit as TH201, and I've also designated a volumetric flow rate and then done the same thing on the other side of the outlet. And what we're interested in is the volumetric flow rate of the water from the geothermal wells. So, all right, let's start going. So our assumptions: steady state, kinetic and potential energy changes are 0, and that's it for now. So let's keep on going. So we know that our volumetric flow rate, it's related to the mass flow rate by this equation right here, right? M dot is equal to V dot over specific volume. So I've just rearranged to get V dot, and I've made sure to indicate that it's for the dry air, or for the air at state 2. All right, so I'm going to focus on the M.A2, and I'm going to define that by applying my conservation of mass to this control volume that I've drawn here, so just the air itself. If it's steady state, dm dt goes away, and I see that M.A1 equals M.A2, and so I could just drop that subscript 2. All right, now I apply my conservation of energy to that same control volume. And I do have heat going into my control volume. I will notice that it is equal to 4.2 tons because the Q dot out that they're referencing, it's Q dot out of the cycle, but it's going in to my air. And so there's my 4.2 tons, and I can rearrange and I can solve for M dot A. I do need to figure out what HA2 and HA1 are, but all I need for that is just my ideal property, my ideal gas tables. Make sure I go to my English units, and I'm looking right here, and you see that I have, of course, had to change things into Rankine, but I just pull off T1 and T2 and plug things in. I do have a few little unit conversions to do since I've got tons, but other than that, I've got 87.5 pound mass per minute. So I can plug that in. Now I need to deal with that specific volume of the dry air at 2. So if I assume I've got an ideal gas, I can apply my ideal gas law. That specific gas constant, I need to figure out what heat is. So it's R bar, the universal gas constant over the molar mass of air. I've got all those things, right? I've got the universal gas constant, I've got the molar mass of air, I've got the temperature of the air at state 2, and of course I need to put that in Rankine, not leave it in Fahrenheit. The only thing I might not know right now is just the pressure of the air at 2, but I can make a pretty good assumption that it's at atmospheric pressure, and I can assume that the pressure at state 1 of the air going into that duct is the same going out, and it's just 14.7 psi. So if I plug that in, do my unit conversions, I get my specific volume. And if I plug and chug, I can get my volumetric flow rate. All right, so now I'm looking at part 2. So the isentropic efficiency, it's the work for the compressor if it operated isentropically over what you have to actually put into it because it doesn't operate isentropically. So H2S minus H1 over H2 minus H1. So I just need to pull off each of those things. So H1, I know T1 and I know P1. If I look in my tables, I'll see that it's superheated. Go to my superheated tables for R22, so that's A9E, and I can pull off the H value there. At state 2, well, let's go ahead and go state 2S. So state 2S, H2S is not actually given to me. However, I do know that the pressure defined for an isentropic efficiency, right? It's the isentropic efficiency is defined between two given pressures. So P2, and if you want to think of it as P2S, are exactly the same. And then I also know that S2S and S1 are equal to one another. So I go ahead and pull off S1, and I see that H2S at S2S and P2, it's superheated. I do need to interpolate, but I get 119.46 BTU per pound mass. And then the very last thing I need to do is get H2, and that's based on the properties that are given to me. So T2 and then P2. And I just look at my superheated tables and pull off the value. And if I plug things in, I get 79.7%. Now I'm ready for the power input. So I've already drawn my control volume around that compressor. I did that before anyway, but I'll show it here. So it's the mass flow rate of the refrigerant, R22, times H2 minus H1. And I already pulled off H2 and H1. I do need to figure out what the mass flow rate of the refrigerant is, though. So in order to do that, I am going to choose to analyze my condenser because I'm given the rate at which heat is leaving that condenser. So I just rearrange. If I apply my first law to that control volume, I get a definition for Q dot out, and I just rearrange things to solve for M dot R22. I do need to figure out what H3 is, and I see that it is compressed because at 75 degrees Celsius, it looks like my saturation pressure is 146.97 psi, and my pressure is 180, so it's higher, which means yes, I'm compressed. And so what I'm going to do is I'm going to use one of those compressed liquid approximations and say that my H value is approximately H sub F at T at 75 degrees Celsius. So plug and chug, watch those units, and I get my mass flow rate of the refrigerant, and I can plug all of that in. And of course, once again, I've got some unit conversions that I need to worry about to get in horsepower, but I get 2.86 horsepower. Now I'm ready for my COP. Shouldn't be so bad. I've already figured out what W dot in is, albeit in horsepower. And then my Q dot out, that's given to me. That's the 4.2 tons. Once again, watch those units, but it's just plug and chug, and 6.92 is your COP. And the very last thing you need to do is get the volumetric flow rate of the water coming from the geothermal well. So I'm going to use the same relationship with the mass flow rate and the specific volume, but I'm designating that it's for the water and it's at the inlet at state 1. I'm going to handle the mass flow rate of the water at state 1 first, and the way that I'm going to do that is I'm going to apply my conservation of mass just to the well water. And I see that M dot of the water coming in is equal to M dot of the water coming out of that control volume, and so that's just equal to M dot of the water, and I'm going to drop that subscript. All right, so the next thing I need to do, well, I still haven't found out M dot H2O, but I'm going to. So I apply my conservation of energy, but I'm going to now apply it not just to the water, but to the entire evaporator unit. And so if I do that, everything cancels out except those M dot H's. And so I've got things going in, I've got water going in, I've got R22 going in at state 4, and then I've got water going out at state 2. At the outlet, the geothermal well into the well, and then things going out, the R22 going out at state 1. And then I just rearrange and I solve for M dot of my water. Now remember, I already got the M dot R22, I've got H1. H4 is the same thing as H3 because it's a throttling process, so I don't have to look anything up for that. But what I might be a little bit concerned about is the enthalpy of the water at 1 and 2. Now, the state of the water coming out of those wells is obviously going to be compressed. So if it's compressed, there we go. If it's compressed, then we're going to use what's called an incompressible liquid approximation. So our enthalpy change, H2 minus H1, and this is an equation that's not actually on your equation sheet, but it is in your book. So if I assume that the specific heats are constant and you've got an incompressible liquid, then this is an equation I can use. And I'm going to get rid of this last term. It's underlined because typically that value is very low. Because, well, number one, you're probably not looking at a big pressure drop. And number two, that specific volume of a liquid is going to be a really, really small number. So a really small number times another small number is going to be a really, really small number. So we're just looking at that C delta T because C is equal to the CP and CV for a liquid. You may or may not recall that from the lecture on specific heats, but that is the case. So if you're wondering where that is for water, you can look in A19. So this is for solids and liquids. We've got water, and we are at an average of 50 degrees Fahrenheit. So 50 plus 460, 510. So you're in between these guys. It's about 1 BTU per pound mass degree Rankine. So with that information, I'm going to plug that in, replace that delta H with C delta T, and I guess I'm about ready. I just plug in my numbers, and the only other thing I've got is that specific volume. So I need my specific volume at state 1, but since I know that it's a liquid, or I'm approximating it as, well, not even approximating, it is a liquid. It's a compressed liquid. And so I can just approximate that as V sub F at T1. So 0.0602 feet cubed per pound mass, and you're getting those out of your saturated liquid tables for water, or saturated tables for water. So plug and chug, make sure you watch your units, and you get 8.6 gallons per minute. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have any questions.